Evidently not. Now let's record it. Computer sound. 1, 2, 3, 4. Let's go.
Maurizio's car slams into the concrete barrier, catapulting him out of the window and hurling him through the air. Maurizio's car slams into the concrete barrier, catapulting him out of the window and hurling him through the air. Catapulting him out of the window and hurling him through the air. Hurling him out of the window.
Okay, so what's pushing him in the direction that he's flying? Okay, guys, just feel free to jump in.
Barrier, catapulting him.
All right, so what's pushing him in the direction that he's flying?
Out of the window and hurling him.
Any ideas?
Catapulting him out of the window and hurling him.
He's getting catapulted
through the air.
What's pushing him in the direction that he's flying?
The concrete barrier, catapulting him out of the window and hurling. Catapulting him out of the window and hurling him. Catapulting him.
So what's pushing him in the direction that he's flying?
Is it inertia?
I'm sorry, say it again.
Inertia?
Inertia. Is inertia a force? It's not. So give yourself 5 points. So what's pushing him in the direction that he's flying?
Him out of the window and hurling.
This guy's flying. What's pushing him in the direction that he's flying? What's pushing him in the direction that he's flying? He's not connected to anything, right? So if that's the case, what's pushing him in the direction that he's flying? What's pushing the ball in the direction that the ball is flying horizontally?
Force.
Okay, what is the force making the ball go horizontally once it leaves my hand? So what's pushing the ball in the direction that it's flying? The answer to that question is nothing, nothing, nothing. All right, so if there isn't anything pushing on the ball in the direction that it's moving, why would the ball keep on moving then? I mean, my car, when it runs out of gas, it doesn't move. Your car doesn't move. So how come the ball keeps on moving despite the fact that there's nothing pushing on it? Create a project from a Chicago student. If it looks like it's done over a lunch break, because it is, that's what the guy told me. It's hitchhiking. I recognize the guy, so I'm giving him a ride. And this is my Ford Tempo falling apart as usual. This was like almost 15, 20 years ago. So you accelerate in the forward direction. The person inside does a push in the backward direction. You put the brakes on, now the person feels a push in the forward direction. Why is it that the objects inside cars move in the opposite direction of the acceleration of the vehicle? Why do you feel a push in the backward direction when the car accelerates forward? Why do you feel a push in the forward direction when the car accelerates backward? How about a head-on collision between a car and an SUV? Which one is going to experience a larger impact force? Is it the car or is it the SUV? What do you guys think?
The smaller car.
Okay, so common sense, I'm going to give you 5 points for that one. Smaller car is going to suffer the most damage, right? All right, so why?
Because the SUV has a bigger mass.
Okay, so SUV is much more massive. Give yourself 5 points. So which means that the damage on the smaller car is going to be bigger. Okay, what else? All right, so which driver is going to be safer in this case? Obviously, the SUV driver is going to be safer. All right, so let's come up with 3 reasons as to why the SUV driver is going to be safer. Reason number 1, the SUV is much more massive, right? It's heavier, so that helps. Okay, what else?
Well, with it being more massive, it's going to have more crumple zones in it.
I'll give you 5 points. And also, it's got a larger crumple zone, right? So that's going to increase the impact time. All right, one more. So it's more massive. It's got a larger crumple zone. So we got 2 so far, and we need 1 more, people. How about the fact that the SUV driver is sitting higher up? All right, so that's going to help because the force is not directly in line with the driver. All right, so being higher up actually helps you better. So that's not going to be direct impact to his body. So three reasons. SUV is much more massive, heavier, larger impact zone, larger crumple zone. It's going to increase the impact time. On top of that, the driver is sitting higher up. So the driver is not in line with the impact force. So those are the factors. All right, so the next question is which vehicle is going to experience a larger impact force? All right, so okay, so once again, we went back to the same question, and common sense will say it's the smaller car because the damage is much bigger on the smaller car. Okay, who wants to disagree? Who wants to say both will experience the same impact force? I know some of you guys have taken high school physics, so those of you guys who have taken high school physics will get to disagree at this point. So which vehicle is going to experience a large impact force?
Neither.
Okay, so Jack, you said neither. Okay, Jack, are you confident enough to defend that both of them will experience the same impact force? Do you want to make an attempt?
I can certainly make an attempt.
Okay, okay. So, how would you justify that? Okay, so both will experience the same impact force because, complete that sentence.
They'll both experience the same impact force because they're slamming into each other. It's not like they're each separately hitting a tree. They're both hitting this like each other, and so I think the force will be shared amongst that whole collision.
Okay, so I'm gonna give you 5 points. Jack, have you taken high school physics?
Yeah,
Okay, you've taken physics before. Okay, so do you recall Newton's third law, the action and reaction law? Okay, so that's known as karma, right? Being a bitch. So for every single action force, there's going to be an equal and opposite reaction force, right? So if Newton's third law is correct, both vehicles should experience the same force. So whatever the force acting on the small car should be acting on the big one. So whatever the small car experiences, the SUV is going to experience the same thing. All right, so this is the summary of the third law. All right, so having said that, Jack, so what I'm going to do is I want you to defend the third law. In a sense, every time I'm just going to take this simple scenario, I'm going to make it a little bit more confusing, and then I'm going to make it a little bit more twisty, in a sense that I'm going to make it a little bit more challenging. Okay, so in the meantime, what I want you to do is every time I change the scenario, say both of them will experience the same impact force because of Newton's third law. Can you do that?
yeah.
Okay, cool. I mean, just you will get confused. I don't want you to give up. All right, I'm going to try to confuse you. Just hold your line. Newton's third law because of Newton's third law. Same force because of Newton's third law. Action and reaction forces are the same because of Newton's third law. Okay, so just follow back to that position, regardless of how confusing this gets. All right, don't change your mind. Can you handle that? Don't change your mind.
You got
All right,
it.
so Jack, let's go. All right, so which vehicle is going to experience the same? Which vehicle is going to experience a larger impact force? It's the same, right? Because of Newton's third law. Okay, so I'm going to change the scenario. SUV becomes a bus, and this car becomes a smart car. Head-on collision. All right. So the amount of force acting on the car is like 100,000 pounds. Will this car apply the same force back on the bus? Yes or no?
Yes, because of Newton's third law.
You got it. Give yourself 5 points for that one. Okay. So let's change the scenario one more time. Okay. Now the bus becomes a train, and then I don't want to waste that perfectly good smart car because of this thought experiment. Instead, I'm going to put you in front of the train. All right. So the train is coming at you at 60 miles per hour. And the train is going to hit you with 1,000,000 pounds of force, 1 million. All right. So will you be able to apply the same force back on the train?
Yes, because of Newton's third law.
Okay. Okay. So you're saying that, yeah, you should be able to, right? Because that's what Newton said. I mean, no one denies that a train can hit you with 1,000,000 pounds of force. And the end result is fairly obvious because you're not going to survive this. At 60 miles per hour, 1,000,000 pounds of force, not survivable. Okay, so what's not convincing is you applying the same force back on the train. When was the last time you applied 1,000,000 pounds of force on something, and how well did that work out? Can you even apply that amount of force on anything? The answer to that question is no. So, I mean, are you going to be able to apply the same force back on the train when you're actually falling apart? A train hitting you will literally break apart. You will splatter all over the place. So, if that's the case, which one is going to be experiencing a large impact force? Is it you or is it the train?
I'm
You want to say, huh?
going to stand my ground here and say,
Okay, you will have to stay on your ground because you're already committed to it. All right, I don't want you to change your mind. Okay, so the question is, you have to go with what Newton said, and Newton will say what? Newton will say, yeah, it doesn't matter what happens to the person still applies the same force back on the train, right? So if that's the case, my question is, where is the evidence? Where is the evidence that you apply the same force back on the train? The reason why I'm asking that question is, Newton lived about 350 years ago. 350 years ago. Did they have trains back then? No. This guy simply didn't see the train coming. So, do you think Newton made a mistake?
no.
All right. So, if you don't think Newton made a mistake, so how do you explain you being able to apply the same force back on the train? And if that's the case, where is the evidence that you apply the same force back on the train?
Well, the train is much more massive, and so the force that it applies on me is very clearly physically evident, but I don't know that it'd be so evident in comparison to the train.
Okay. All right, Jack, I'm going to give you about 30 pounds. I'm going to give you 30 points because number one, you held your ground pretty well. Number two, you kind of thought about it and you were thinking, wait a minute, there may be a way to explain this, right? Explain yourself out of this. Okay, so we'll get back to it again. This is a bit of a mind twister because Newton says the action and reaction forces should be the same. If that's the case, where's the evidence, right? When you're getting hit by a train. All right, so, all right, clearly we're discussing Newton's laws of motion. So Newton, according to a legend that he himself started, this is a bit of a made-up story, and he told this story late in his life because somebody wanted to know how he started thinking about gravity, because he came up with the law of gravity, laws of motion. Along the way, he also invented calculus. And according to a story that he himself started, he said he was asleep on an apple tree in his family orchard one day, and then the apple falls hits him in the head. He opens his eyes. He sees an apple hanging from a tree, and next to the apple, he sees the moon. He knew why the apple fell. It fell because of gravity. His question was, if objects fall because of gravity, why is it that the moon is not falling from the sky? Now, that question became his obsession. In order to answer that question, he first came up with the 3 laws of motion, and then eventually he came up with the law of gravity. And then in order to solve this puzzle, he also invented calculus. He was only 21 to 22 years old when he had done all this stuff. The first thing he did, he borrowed the first law from this guy, Galileo. Galileo was conducting some interesting experiments that he became famous for. Number one, he was in his 70s. He was under a house arrest. And his obsession was this: free fall. Remember free fall? Objects falling under the influence of gravity? But he knew the falling objects would accelerate, but he didn't know how to measure this acceleration. The reason why it's so difficult to measure this acceleration is because of the fact that the motion happens real fast. You can't even tell if it's falling at constant speed or if it's speeding up, right? So this guy, being a genius that he was, he decided to slow the motion down. You're thinking, how do you slow it down? He's thinking, oh, it's easy. I'm going to use an incline. So if you use an incline, what do? You roll it down. You roll the ball down. It slows down. It's still rolling down because of gravity. Now you can measure the distances within subsequent time intervals, 1 second time intervals. You look at the distance, measured distance. The second measured distance is going to be larger. The third one is going to be larger. And then eventually, by modifying the mathematics, you can figure out what that acceleration is. Some that we will do later on. So when he was doing that experiment, all of a sudden he noticed that something interesting, intriguing. So he's an old guy, so he had one incline, the second incline to catch the ball. And then he lets the ball go down, and then the ball just keeps on rolling and goes back up to the same point. I mean, if you ignore the effects of surface friction, the ball is always going to go back up to the same height. He says, that's weird. It puts the second incline further away. Once again, the same observation. His question at this point is, what's happening when it's on a flat surface? What's happening when it's on a flat surface is this ball keeps on rolling, right? It keeps on rolling. It keeps on rolling in a straight line at a constant speed. So the question is, what's pushing the ball in the direction that it's rolling, if that's the case? What's propelling the ball in the direction that it's rolling? The short answer is nothing. Nothing is pushing on this ball. There's no push acting on it. There's no force acting on it. There's no pull acting on it. Yet this ball keeps on rolling in a straight line at a constant speed. He says, if you were to get rid of the second incline and get rid of all the obstacles in front of the ball and ignoring the friction surface, this ball is going to keep on rolling in a straight line at a constant speed forever and ever and ever. The question is, why? What's pushing the ball in the direction of the motion, in the direction of this motion? If nothing is pushing on the ball, and obviously nothing is pushing on the ball, why then the ball keep on rolling in a straight line at a constant speed? The answer appears to be fairly straightforward. He said the ball is going to keep on rolling in a straight line at a constant speed forever and ever and ever in the absence of an external force because it's got a tendency to do so. All right, objects have a tendency to retain their initial motions. About a generation later, someone named Descartes decided to call this inertia. Descartes is a French philosopher and a mathematician. So the person who coins the term is Descartes. The person who came up with the concept is Galileo. So what's the meaning of inertia, if that's the case? Well, inertia means two things: and a tendency to retain initial motion, or it means resistance to change in motion. Okay, which means that the object at rest, in the absence of an external force, is going to remain at rest, and the object in motion is going to remain in motion, meaning that it's going to keep on moving in a straight line at a constant speed forever, unless acted upon by an external force. So in the absence of an external force, the objects will retain their initial motions. Object at rest remains at rest, the object in motion will remain in motion.
An obstacle as common as a mailbox can be absolutely deadly.
Mailbox wants to stay at rest, so which means that there's going to be a resistance to change.